No, the answer is, I understand your question. The answer is they could get here on a time scale of a few years if they can travel close to the speed of light. From their vantage point, time compresses in terms of travel time. You travel close to the speed of light. This is always the way people get around interstellar space travel. You build a rocket which goes at 0.999 c, and I travel from here to the center of the galaxy in 15 minutes if I want to. But it's 15 minutes on my watch, not on the clock back on Earth. It's still going to take 30,000 years to get there and 30,000 years to go back if I'm watching a clock on Earth. But on board my ship, it takes 15 minutes. So I come back and the Earth is 60,000 years older, and I'm a half an hour older. That's special relativity. That's a wholly different topic.
So you're telling me that I do need to keep worrying about people coming to visit us?
Yes.
What about signals?
Let me, because I don't want to run over time because people I know are already getting glazed over. All right. Here's a plot. You can go online. There are websites which update the data on every planet found every day. So if they improve the observations, they improve the velocities, they improve the masses, they update the catalog. You can get any star you want to, any problem you want to, and pick out the sample of information about that entire sample of planets and plot it up any way you want to.
Is that the data you work with?
I don't work with it at all. I don't do this stuff.
Okay.
I don't care about planets. I care about stars. There's a whole nother talk dealing with what Kepler tells us about stars. That's not this one. Okay, so here's an example. This is the mass of the planets found in units of Jupiter masses. So that planet has a mass of about 47 Jupiter masses. That one's 80 Jupiter masses. So this is mass along here, and this is the period, the time it takes to go around the star once, the orbital period. And you can see most of the planets being found are 10 Jupiter masses or less. Fine. But the periods go all the way from 0 up to 10 years. What we're trying to find is Earth. I don't care about a planet that takes 10 years to go around a star. I want something like Earth. So let's narrow down the plot a little bit. Now the planetary mass goes out here. This is 1/20th the mass of Jupiter. What's the mass of Earth relative to Jupiter? Anyone know? It's about 3.03? No, 0.003. So there it is. This is Earth on this plot. Its mass is 0.003 of Jupiter, 3,000ths, and it's got an orbital period of 1 year. What you'll notice, there's nothing else up there.
There's nothing there.
We're it. This is a selection effect. This is a bias. Because if you're going to try and find an Earth-like planet close to the star, your sample is not going to see it very easily using this technique. So this is primarily a selection bias in the way the sample is produced. The key point, though, is there are tons of planets which have Earth-like masses in this plot. They just don't all orbit far enough away from the sun. These are all orbiting inside the orbit of Mercury. So they're really close to the star.
Oh.
Okay?
They're hot.
They're hot, which makes them not very good for life.
Well, if you've got a hotter star, though, then you could just, if you got a planet that's farther out, you don't have to keep those distances the same.
The habitable zone,
Yeah, the sweet spot.
the sweet spot.
Yeah.
You find this by saying, I put the planet next to this star. How far away do I have to put this planet so that its temperature and conditions are just right? The big thing people will look for is liquid water. You don't want it too cold so the water freezes. You don't want it too hot so the water evaporates like Venus. You want it just right. And where you find that zone will depend upon how hot the star is. It's a really hot star, I can put it further away. It's a really cool star, I can put it closer. So let's go through this sample and identify all the planets we found so far in the right habitable zone. This is showing you the temperature of the star, about 3,000 degrees, the sun 6,000 degrees. Out of the entire sample we've found so far, here are the candidates. 1, 2, 3, 4, 5, 6, 7. 7 potential planets in the right distance away from their star to be in the sweet spot. But the other point you should notice about this is the size of the figure. The size of the planet is telling you how massive it is. Look at the plot. Big, 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 big. planets we found so far in the right sweet spot are all 2 to 3 times the mass of the Earth. They're called super-Earths. Yes. So they have the right temperature, but they're massive. They're not like us. Is that important? We don't know. Gravity is important. So we don't know if they're going to have life. But if you're going to try to look for a spot to find life, those are the planets you want to study. Not the ones that are going to sit over here, but the ones that are going to sit over here. So even after 5 years of work and a few thousand observations of stars, we have a sample of maybe 5 to 10 to pick from. To study in more detail. Last slide, I promise. It looks confusing. Simplify. We're going to break up the planets we found into 3 pictures. The ones which are in the hot zone. They're so close to the planet, they're burning up. I don't care what kind of star it is, it's just close. So close, the planet's hot. Then there's a zone which is a habitable zone, where the temperature's just right. And then there is the ones that are too far away and they're cold. All right, that's the first thing. Second thing, though, is planets come in different sizes. There are planets which are like Earth or smaller. There are planets like Jupiter and bigger. And strangely enough, there are planets in between called sub-Neptunian planets. They have masses higher than the Earth, but less than Neptune. The amazing thing about it is we have no planet like that in our solar system. We always thought we were typical. But there is no sub-Neptunian planet in our solar system. But let's look at the data. You can see most of the planets they found so far, look at the numbers, 4, 148, 599, 18, 9. These are all in the hot zone. Our sample is totally biased toward things near the star, because it's easier to see the effect that way. But even on this sample, hot Mercuries, subterranean, Earth-like planets, super-Terran planets, hot Neptunes, hot Jovians. The super-Terrans or the sub-Neptunians, we have nothing like this in our solar system. This is the most common form of planet. And all the other solar systems we study out there, this is the one that swamps everybody else. We have nothing like it in our solar system. You go down here. Here is the habitable zone. 0, 1, 7, 91. 72, 44. Again, the most common one, somewhere between Earth and Neptune. Go down here, the cold zone, so far away. Again, this is a selection effect. Well, the numbers are so small, 0, 0, 3, 6, 4, 1. So the most common form of planet in the universe is something we've never seen before. And we are not typical in that sense of the word. Our solar system doesn't resemble all the others out there. So in that sense, we're special. The question is that crucial to making life on a planet? The answer is we don't know. We've just started this. So the hope is in the next 10, 15 years, as more and more of these get studied up close and personal, we can find out whether or not they show the signs, the signature of some potential life form.
Given where the data is at right now,
Yeah.
can I use all of this to debunk my brother-in-law's belief in extraterrestrial beings?
Yeah,
Okay.
sure.
Yeah. I mean, it seems-
There is zero evidence that we've ever been visited by anything.
Absolutely.
Yeah. Questions? Yeah.
Are the larger planets, or can they figure out, are they mostly gas giants
Yes.
like ours too?
Yes.
Which makes them less likely to be habitable
Bingo.
by us?
It's like taking Jupiter and putting it where Mercury is. One of the major breakthrough discoveries of this entire survey of planets, which no one expected, is to find Jupiter, Neptune-like planets in where Mercury is around the sun.
Oh.
Nobody expected that. But it's important because we know they didn't form there. There's no way you can make a Jupiter where Mercury is. It's impossible. So we believe now that those planets were out here in the outer portion of the solar system. Because of dynamical interactions, they slowly slide in toward the star. And eventually they get torn apart by the star and blown away. But while they move, they'll sweep up everything in their path.
But we're
Compacted,
talking,
it's
we're talking
gone.
massive time period.
Yes, we're talking about millions of years, literally.
Billions of years.
Yeah.
You answered Dennis by saying there's no chance for extraterrestrial beings. That was my question, really. Will we ever be visited
Never say never.
by
Yeah, I can't say never, but my answer would be no.
And then, I mean.
There's one way to get around, I'm sorry. the problem we always talk about is the time it takes to go from here to there.
Right.
Oh, yeah.
Right?
Because you'll
But-
die before you
Right,
get
but
there.
how do I know there aren't life forms out there where a million years is like a day?
Right.
They make a ship, they want to travel for a million years, fine, I can do it. I'm going to live for 5 million. I don't know if they don't exist. But based upon normal lifespans of centuries as opposed to millions of years, the answer is 0. The other real problem most of the time is the energy, the cost. We can send a spacecraft, a small spacecraft, to the nearest star today. But it would take basically the GNP of the world for the next 10 years to build this spacecraft. And no one's going to do that. So there's a cost thing, and there's also the time thing. So the answer is technologically, yeah, it can be done, but no one in their right mind would do it.
Well, I developed a theory along the way that maybe there is no other life forms out there because God saw what we've been doing to this planet. And he says, man, I've got to get out of this planet.
That took a little too long. I mean, you got 4 billion years before you got there, so it's a long time to have things mess around before you decide you made a mistake. Other questions? Yeah, go ahead.
What does this study
Yeah.
tell an astronomer or cosmologist about the larger universe?
No. It has no impact whatsoever on cosmology, right? Because you're talking about phenomena on a planetary individual stellar basis. So in that sense, it will tell me where changes might occur in a solar system where planets have formed and how they'll evolve over time for a given star. But the planets themselves do not change the way the star evolves, all right? So that's not a problem. The bigger picture, and again, I didn't talk about this because it's a whole nother talk. The other reason why you do this kind of study is if you observe a star over time, the star will change in brightness. Has nothing to do with evolution. I'm not talking about it changing because it's burning out of fuel. I'm talking about the sun. The sun today is oscillating. It rings constantly like a giant bell. The analogy most often used is you've got a 1,000,000-string guitar, and you hit all 1,000,000 strings at once, you get all these frequencies coming out. The sun does this every minute of every day, nonstop. And the beauty of it is, if I monitor the brightness changes of the sun, and this has been done, I can actually measure the oscillation frequencies of the sun caused by this oscillation. The example most often compared to is seismology. I have an earthquake off in the earth. I measure the waves that come through the earth out of the earthquake, and I can tell you what's below the surface. The density of the rocks, how hot they are, how liquid they are, what they're made out of. You do the same thing with the star. You monitor its brightness, and the brightness changes on really small levels, but if you monitor it for 5 years, I can go in and pick out the frequencies where it's repeating over and over again. That tells me how this bell is ringing, and by telling how the bell is ringing, I can tell you what the bell's made out of. I can tell you how hot it is, going from the surface down to the core. I can tell you what it's doing inside the interior. So people have used this data, not the planets. The planets are junk. You take away the planets, and I look at the light curves over time where the planets were moved. And I can tell you the mass of a star, I can tell you its temperature, I can tell you what's going on inside its core in terms of nuclear fusion. That's important. Because now I can test my explanation of stars and their structure with real observations as opposed to inferring what it's supposed to be like.
And that's from 160,000 stars.
160,000 stars, yeah.
The solar flares
Which is
mess up that
minuscule.
data.
Well,
They can, but they're random. That's the beauty of it. The kinds of frequencies we're talking about are repetitive. Exactly. You remove it as background noise. Yeah. Yeah, go ahead.
Well, this isn't a planet question, but,
Yeah.
well, I just heard on NPR, an astronomer being interviewed about, he or she was talking about the edge of the universe, the notion of the edge of the universe.
Yeah.
What do you think? What's your thoughts?
What they're referring to, there is no physical edge. You don't suddenly run into a wall and bounce off of it, right?
No, right.
What they're referring to is how far out in space can you actually observe and detect something. The problem you have is light has a finite speed. So if I'm standing here, I mean, sound works the same way. You're in a concert hall and someone's playing on stage. The people in the front row hear it first, the people in the back row hear it last, right? Same thing happens with light. Bang, a star blows up over there. It's 5 million light years away. It's going to take 5 million years for the light to get to me. So when I finally get the light, I'm seeing the explosion as it was 5 million years ago.
Right.
Well, the problem is the universe is 13.725 billion years old. which means if there's a point out there 14 billion light years away, anything from that spot, even if it left at t equals 0 when the universe first begins, hasn't gotten to me yet. So I can't possibly see that region of space because the signal's still traveling. So that gives you an observable edge.
Yeah, that's what she was talking about.
Yeah, that's what she's talking about.
Then the question really is the universe expanding or is it in a form of entropy coming in on itself?
It's still expanding.
It's expanding.
That's the way.
It
You're
depends.
taking the space and actually stretching it over time.
Yeah, that's what that person's also talking about.
Yeah, the space itself is stretched. The space-time is being stretched because of the expansion of the universe. The actual galaxies don't move. The analogy most often given in textbooks is you see the galaxies moving away from each other. The galaxies don't move. They're stationed. They're attached to the space. It's a space that stretches. And it gives the appearance of the motion of the galaxies. The galaxies don't move. Okay?
Galaxies.
So what's the answer?
We're expanding.
What?
We're expanding.
The universe is
And it's going faster and faster and faster. Which is really weird.
Multiplying?
Yeah, it's accelerating.
But is it getting, is it increasing in its mass?
No. So the infinite long time distance, you'll basically find all the galaxies isolated from each other.
Yeah,
One here, nothing else in the universe.
right. Okay.
And long term beyond that, same thing happens to all the stars. One star, nothing else around it, yeah. Kind of a lonely universe, but I'll be dead by then, I'm gonna care. Other questions? I've already kept you here long enough and berated you with,
I want to tell you that this is the most exciting hour I've spent in years.
there's a side
Yeah,
commentary there, but then,
My little brain can't hold the whole universe inside, but I know passion when I hear it, and you've got it. And I'm sitting here wondering how you've got that passion for the universe.
what can I say?
Your parents.
It goes back to when I first started learning this, and the simple fact of the matter is, I don't understand how anybody can't get excited about this.
Yeah.
I mean, how they can't get excited about this. Yeah, I teach students all the time at KU, and the first thing I try to get across the first day, because most of them come in and they want you to go through the usual nonsense. All they care about is a multiple choice exam they're going to get in 3 weeks. I don't give multiple choice exams, which means my class drops very rapidly. But they're concerned about getting their grade and getting out. But you sit there and you tell them, look, you live in a universe. It's like growing up in a small town in western Kansas, which has never had any communication with the outside world. You've got no phones, you've got no internet, you've got no TV, nothing. You live in your little community and you are raised by decent people and you grow up thinking you got it all. You understand it all makes sense. You figured out your universe. And then somebody takes you out of that spot and puts you in Paris. You're going to go nuts. But the critical point is, how can you figure out what your role in the universe is if you don't know what the universe is? So the notion that all you have to worry about is what I know about Lawrence or Kansas or the United States just drives me nuts. Because I don't think you can have a coherent picture of what you are in the context of the universe, again, if you don't know what the big picture is. And most people don't know the big picture beyond what they hear from Neil Tyson on TV. So.
But Phil, I have another story about why I enjoy physics. The last year I was teaching physics in a 40-year career. I was teaching a junior-senior course in electromagnetic theory. And the textbook had a section on the theory of the rainbow, which Descartes had actually figured out quite a few years ago. Well, I sat down that morning, it was an afternoon class, and spent a couple of hours, and it's not even terribly complicated physics, and uses a lot of high school geometry. And then showed the class how to do it. And just using physics, you can predict that there's a secondary rainbow and that the colors are reversed in it. And I think I came to the forum at lunch and I told people I spent a cultural morning because this is a marvelous world, and if you can understand it in more ways, well, it's a richer world.
Sure, yeah. It's simpler. It looks complicated to the average person out there because...
Well, it's more beautiful.
Exactly, yeah. It makes more sense, yeah.
the human being is a great development. And being able to use your mind to understand something like this instead of just looking at it, well, that's another level of enjoyment.
Again, thank you for your time. I
Thank you.
apologize for running over a little bit.
Thank you.